Yeah. Okay. That's right. Okay. So thank you everyone for being here. Um, my name is Abhishek Kumar. I am a PhD candidate at Indiana University. Uh, sorry. I'm a PhD candidate at Indiana University. I'm going to talk about the Floquet gauge pump. And this work is based on our latest preprint, which is available on archive. Um, and this work has been done in collaboration with Professor Gerardo Ortiz, Professor Philip Richerme, and Professor Babak Seradjeh at Indiana University. So also, like, you can either interrupt me anytime when you have a question, or you can wait till the end to ask the question. Either way is fine for me. So let me start with the motivation of our work. So in non-interacting topological system, bulk boundary correspondence holds for the most of the system. The bulk boundary correspondence means that corresponding to a non-trivial bulk topology, there exists some localized boundary states. And often in an experiment, this is used as a signature. The boundary mode is used as a signature for the bulk topology. In interacting topological quantum system, our understanding about the bulk boundary correspondence is even limited. We don't know exactly whether that holds or not. But even the notion of topology depends on the choice of the local basis. Like in fermionic representation, something may look like topological things, but in other case that might let's say in a spin case, a spin representation, that might not be the case. But the thing is, the degeneracy of many body ground state does not depend on the choice of local basis. So we would like to have a probe that could either detect the bulk topology or detect the ground state degeneracy. So we will be so for that purpose we are proposing a probe that can fulfill this criteria. Okay, so I'll first give a general setup of gauge pump and Floquet gauge pump, and then I will demonstrate that using a concrete model. So gauge pump is a specially resolved probe that is employed to detect the degeneracy or bulk topology or spontaneous symmetry broken phases of gapped ground states. So to construct the gauge pump, we take two gauge equivalent system and then connect them with a bridge. Then we look for some observable that depends on those gauge parameter and will be useful for detection of this topology or degeneracy. So mathematically, you can write the Hamiltonian as given here, and you can gauge out all the gauge parameters from the left side to the bridge Hamiltonian. So we can derive the gauge current. So one observable is like the gauge current, and we can derive the gauge current in terms of either initial Hamiltonian or in terms of the bridge Hamiltonian after gauge transformation. An example of the gauge pump is Josephson junction for trivial or topological superconductor. So we know that if we have a Josephson junction, and if the two superconductors are trivial, then we get a 2 pi periodicity in the phase difference. If the superconductor is topological, then we get the 4 pi periodicity in the phase difference. So this is often used as kind of used to detect the topological or trivial property of a superconductor. Theoretically, we can also construct this gauge pump in any metric space, like in you can do it momentum space also. But for experimental purposes, it's always good to think this in a spatial, in real space. Okay. So this is different from what we also know about the, know about the Thouless pump. So in Thouless pump, we have some confining potential, and we have two reservoirs, and we have some periodic confining potential, and that depends on some parameter. And we change the parameter adiabatically, then we can transfer the charge or particle from one side to another. In case of gauge pump, we even just the difference in the gauge phases can produce a current. So before going to talk, before I will talk about the Floquet gauge pump, I will give a brief primer for Floquet theory. So in Floquet system, we have a time periodic Hamiltonian, and solution to the Schrodinger equation can be written as a phase factor times a Floquet state, which is periodic in time. The phase factor contains the quasi energy, which is only defined up to modulo omega. If you plot the quasi energies with respect to some quasi energies with respect to some parameter, then you will see that the quasi energies will repeat after omega in energy excess. And with this different omega zone is we call the Floquet zone, and one of them is the principal Floquet zone, where the quasi energy there is no additional energy, just quasi energy kind of. We can, so in this case, the time evolution operator can be decomposed into two parts. One is the micromotion operator, and the second term is a stroboscopic time evolution operator. So micromotion operator tells the evolution of a state within one period, and this stroboscopic time evolution operator tells us about the evolution of a state at integer multiple of time period. So in a way, this HF governs the dynamics of a state stroboscopically. So in general, calculating a Floquet Hamiltonian is difficult, but in high frequency limit, we can use the Floquet Magnus expansion or some other expansion to calculate the Floquet Hamiltonian. Here the Hn are basically Fourier coefficient of Hamiltonian. Okay, so now I will talk about the Floquet gauge pump. So Floquet gauge pump is idea where we consider one system, and then we drive the system on left side and right side differently. Then that drive can create a breeze within the system, and then it now becomes equivalent to our original gauge pump idea. But obviously, the whole system has become here become the time dependent. And in this case, we can derive a Floquet gauge current, which depends on the Floquet state and many body quasi energy of the system. If we want to just calculate the time average Floquet gauge current, then we just need to calculate the quasi energy of the system, and then we can look at the time average Floquet gauge current, and we can tell some property about our initial system. Okay, so having described the general setup, now I will consider a concrete model where I will implement this idea and calculate different things. So here we consider a 1D XY model. So initially we can consider a static 1D XY model with transverse field. Then we apply some drive on left side and right side differently. So overall, the total system becomes the time periodic, and we can write the Hamiltonian like this. So here, this J bar XY are a static term, and delta is basically oscillating part, delta J. And this, in a static case, at 0 temperature, in thermodynamic limit, we know that this has quantum phase transition. When Jx plus Jy is greater than H bar, then we get an ordered phase, and there are 2 degenerate ground states. While in opposite limit, we get a disordered phase where we have only single ground states. So we will find the Floquet Hamiltonian for this periodically driven XY model in high frequency limit, and we will use the Floquet Magnus expansion. So when the Floquet Hamiltonian in this case, you can see that there are some additional interactions in the system apart from the static one, and these basically parameters involved in this additional interactions only depends on the drive parameters. Like this zeta A or xi A, these are the only dependents on the drive parameter. And they are in interaction. You can see that we also get a Dzyaloshinsky-Moriya kind of interaction. But like diagonalizing a spin system is really hard, and even numerically it is very hard. So for that purpose, we will to overcome that problem, we will go to fermionic representation and try to diagonalize the Hamiltonian and calculate the quasi energy, so that we can calculate the time average Floquet gauge current. Okay. So we will use the Jordan-Wigner transformation to go from spin operators to the fermionic operators. And Jordan-Wigner transformation is a non-local transformation which map a spin half system to a fermionic operators. When we do that, and we also after doing that, we also do some gauge transformation on left and right side. Then we get Floquet Hamiltonian in terms of the fermionic operators as some like 2 Kitao chain on left and right side. I mean the Kitao chain on left and right side, and there is a connecting or bridge Hamiltonian in the middle. So this HFA is basically Kitao chain, and Kitao chain is basically 1D P-wave superconductor, a spinless P-wave superconductor, and it can be either trivial or topological depending on the parameters, depending on the value of parameters. So it is written here. and in case of topological superconductor, it contains the two Majorana modes at the end. But if we look at the Brise Hamiltonian, then we see that this is kind of different from what we usually get in a Josephson junction. So here you can see that there is a WB and there is a delta B term. So in usual Josephson junction, we get only the WB, like hopping term, but now in this case, we get a pairing term also. So this is, we call the unconventional Josephson junction, because you have the hopping and pairing term both at the bridge. Okay, so we can also see that all these parameters in this WA hopping and pairing parameters and chemical potential can be written in terms of the spin parameters, static and driven, both. And moreover, we can also see that the phases at the total phase at the bridge can be written in terms of the drive parameters, and we can manipulate those phases by just changing the drive parameters. So here there is a plot where we have changed the drive parameter, and we get some range of a good range of hopping and pairing phases just by changing the drive parameter. So that's kind of the main message, that these phases can be easily controlled by this drive parameter, just by changing the drive parameters, which will be useful in detection of basically topology or degeneracy. Okay. So so now we will look for a we will derive the time average Floquet gauge current analytically. So to do that, we will consider the left and right side of Hamiltonian as unperturbed system, and the Brise Hamiltonian as a perturbation. So a true ground state in Floquet system is not well defined, but since we are considering the high frequency, we will stick to a one particular Floquet zone, and then we say the ground is we construct a ground state by filling some lowest energy states. So so in that respect, we get the phi naught corresponding to the unperturbed system, and the quasi energy we can write it as the sum of unperturbed and perturbative energy. The perturbative term up to second order is written here. We also write the Brise Hamiltonian HB in terms of the Boglev quasi particles, and the transformation is written here from the CL dagger to the gamma L dagger and gamma L, and similarly CR dagger, the left and right side. Okay, so when we do that, we get like, so also this perturbative quasi energy depends whether the unperturbed system is trivial or topological. So if unperturbed system is trivial, then we get the second order. There is no contribution from there is zero contribution from the first order. Only we get the second order contribution. And after calculating the quasi energy, we can get the left and right gauge current, and which we get here. And here we see that this different coefficients depends on the WB and delta B. So all these dependence are quadratic in nature. So we can analyze this formula like when we have the delta B equal to 0 and W be non-zero, then this is the usual Josephson junction, where you get the current as so here the 2 phi h is basically phi h is phi L minus phi R over 2. So in that sense, it's still 2 pi periodicity. So we get the usual Josephson junction, and in this process, the process involved is the Cooper pair tunneling. The other case is like when we have delta B non-zero, but WB equal to 0. Then we see that the left and right side current are same. There is no negative sign. So in other previous case, there was loss in one side is gain in other side. But in this case, it is both sides have the same sign. So this here the process involved is Cooper pair co-tunneling. So what happens is like the Cooper pair from both sides goes into the bridge or goes out of the bridge, either way, depending on the sign. So that is kind of a kind of unusual Josephson current that we get. Also, theoretically, like if you keep the phi p equal to constant, one can get a 4 pi periodicity even in case of trivial case. So in this kind of situation, the 4 pi periodicity. So in 4 pi periodicity may not be a good good clue to say that whether the system is topological or trivial if you have the delta B and WB non-zero. Okay, so for topological case, we get a first order perturbative energy, and you can see that the formula is this coefficients here are linear in depends linearly on delta B and WB, and P naught is basically P naught is parity in a degenerate ground state. So phi naught is here is like linear combination of degenerate ground state. So here also like if you keep like delta WB non-zero and delta B 0, then you will get the usual fractional quantum fractional Josephson current. And here the process is Moirana quasi-particle tunneling. But if you have like delta B non-zero but WB 0, then you get something the Cooper pair is splitting. So the Cooper pair in the middle, the bridge is split, and it contributes to the current on both sides. So you can see that like these things in at least in fermionic language can detect the topology or so for trivial phase the gauge current depends quadratically on a hopping and pairing amplitude, but in topological phase it depends linearly on hopping and pairing amplitude at the bridge. Also, if you plot them, plot the gauge current with respect to hopping and pairing phases, then you will see that there is a discontinuity in case of topological phase if the initial state does not preserve the parity, but there is no discontinuity in case of trivial phase, no matter what initial state you choose. So now we will, so having derived this analytical result, now I'll focus on the numerical parts, which validates those results. So here I plot the left and right gauge current, and I have scaled it with respect to WL square in case of topological case, and trivial case, and in topological one I have scaled it with respect to WL, and it shows that they are linearly dependent in case of topological phase and quadratically dependent on in case of W in case of trivial phase. Also, you can see that there is a discontinuity in the graph. Like if you go even diagonally, then you see that it changes value from, let's say, -0.3 to 3. Those are basically related to the change in parity. So, but there is no such kind of discontinuity you will see in case of the left or right, in case of the trivial phase. So similarly, you can look for the right gauge current also. We can also plot the total gauge current at the bridge, JL plus JR. In this case, we can see that in trivial case, there is no discontinuity. But in topological case, we see this discontinuity because of this parity change. And this plus minus shows the parity of the system with respect to this phi h and phi p. We can, so since we have started these things in terms of the, started this thing with a spin operator, we would like to go back to our spin language, and there we can calculate the gauge current that we have calculated here is in a spin language is magnetization current. And we can see that in case of in there also, like, so if you when you talk in terms of the spin, we have two phases, ordered and disordered. And in ordered phase, you can see that there is a sharp discontinuity in the gauge current, but in disordered phase there is no discontinuity. So this could be used as a probe to detect the ordered phase or disordered phase in a spin system. So I'll give the experimental signature for this periodically driven XY model in ion trap setup. So to see that whether a static XY model is ordered or disordered, we can measure two quantities. One is the average magnetization current, and other is the parity, which in a spin language is multi-point spin Z correlators. So when we measure the average magnetization current, then as I said, you will see either the discontinuity in case of ordered ground state, or if you just plot the left and right current, then you will see the 4 pi periodicity. But in disordered case, you'll see no discontinuity in total current, but there is a periodicity. There is a 2 pi periodicity in left or right current. Also, if one can measure the a spin multi-point spin Z correlator, and if you consider the system, if you consider the ground state as the lowest energy, all the lowest energy, I mean depending on the number of a state, like you just, if you consider a ground state which does not preserve the parity, then you will see that in case of disordered phase, there is no change in parity. So if it is 1, it is always 1. If it is -1, it is always -1. But in ordered phase, which is degenerate, we get the change in parity if we change the drive parameters. So that's kind of a that can be realized. I mean, so these things can be realized in experiment, and using this by changing this drive parameter and measuring these two quantity, we can detect whether the system has the ground state has degeneracy or not. Um, Also, like as I earlier mentioned, that whether if we prepare the initial state where the ground state does not preserve the parity, then sorry, if the ground state preserve the parity, then you do not change the you do not see the change in parity if you change the Derive parameter, but you will see the 4 pi periodicity in that. Okay, so now I'll conclude my talk and say something more about the interaction. So I have described the general setup for gauge current and Floquet gauge. General setup for gauge pump and Floquet gauge pump, and then I took a time periodic 1D XY model with transverse field. There I obtained the Floquet Hamiltonian in high frequency limit. And when that Hamiltonian is written in terms of the fermionic language, then we get an unconventional Josephson junction. So I derived the analytical results for the gauge current in that case. And I also saw the numerical results for gauge current and magnetization current. And also I give the I talked about the experimental realization and detection in ion trap setup. So we can also think about the adding the SGSG kind of interaction. So if we add SGSG kind of interaction, the current operator will not change, but then we have to just think about the ground state. If the ground state has the same degeneracy as when we have the XYZ model and with transverse field, and it has the same ground state degeneracy as for XY model, then we can use this to detect the degeneracy for XYZ model also, because the operator does not depend on SGSG kind of interaction. Okay, so thank you. I will now take some questions. Yes, someone. Do I have to unmute?
No, I can unmute myself.
Oh, yeah.
So the question is about maybe first half of your talk. Could you please? I just didn't get it. Could you please say why was there a problem of finding ground state in Floquet formalism? Maybe I didn't understand something. You told like it's not possible.
Yeah, so like that. Yeah, so the problem is because of this. So as you know, like in Floquet case, we do not have a energy conservation. We have something called quasi energy, but the quasi energy is only defined up to the omega, up to omega frequency.
Mm-hmm.
So that you can see, like if you add this, like e to the power I omega t, then that time you can also you add some energy omega, and then what you will see that that come you can observe this e to the power I omega t in now in a state. So you again get the same factor, like the epsilon n omega plus some state which is periodic in time. So because of that, like there is the ground state is not well defined. So what we are talking is like we take a particular Floquet zone, and since it is a high frequency, like and also there is no, I mean there will be less problem of heating. That's a different subject, but yeah, in high frequency limit. So we are just like filling the lowest energy state, similar to the static case. But the problem is here is that there is no like
so you take a certain zone and then find the ground state there, right?
Yeah.
Okay, thank you.
Any other question?
I guess I can ask a question.
Yeah, sure.
So at the end, when you were talking about the interactions,
Yeah.
can you say a little more about what kind of interaction? So SCSC, so the XY model is nearest neighbor. SCSC here, does it need to be nearest neighbor or?
No, it can be like long range also. So because like this operator we are calculating, always commute with the SG. Basically, the magnetization we are calculating the magnetization current, which is like the commutation of your Hamiltonian with SG. So no matter, you can take all long range in SG. It doesn't matter. At least up to operator term. Like if you just look for a gauge operator. Gauge current operator.
Right. So the operator, the gauge operator doesn't change. So you're saying with a system that has SCSC, even long range SCSC interaction, it's still the magnetization current that will give you the gauge current.
Yeah, as long as because there are two things. One is the gauge current operator. Other is the ground state. So if we know that the ground state has the similar or they are connected or even to the XY model, then yes, it can detect. But it depends on ground state also.
Right.
Okay, then I will, if not, if there is no any other question, then I'll stop sharing.
Okay, thank you. Should I stop recording?
Yeah. Yeah.